I am director of Nordita, the Nordic Institute for Theoretical Physics, so I thought I would start with a picture of myself on the Nordita campus. On either side of me in this picture are yellow buildings that make very nice offices, but the history is kind of fun. Namely, they used to be hospital buildings when this part of town was way outside of Stockholm, and so I think I'm in leprosy. And the next building over is typhus, and the one we just acquired, typhoid, so infectious disease is well represented here. But anyway, so my talk is obviously rather different from what we've, the focus of this, of Congress, and it's also quite a title, What Do We Know About the Universe? So I'm going to tell you a little bit about cosmology, going back to the origins of the field in 1915 with the work of Albert Einstein. So there have been creation myths since antiquity, but the one that we've had now for 100 years is a good one. I think we've nailed it. The hot Big Bang is right. So this all started with the work of general relativity, and pretty soon after Einstein's theoretical work, then there were follow-ups of how do we apply this to the universe as a whole? And out came a picture that the universe could be contracting, expanding, static, a wide variety of possibilities. Einstein actually liked the idea of a static universe because it has this additional symmetry of not changing in time. So the basic ideas of Einstein's work is that there's a connection between the mass-energy content of the universe and the space-time geometry. So as illustrated here, there's the equations of relativity. So on the right-hand side, you have the mass-energy content of the universe, and on the left-hand side, you have the geometry. And these two things are related with Newton's constant in there. So I keep pushing this button too soon, but one of the consequences immediately was that mass bends light. So you've got the sun en route from some distant star sending light to Earth, and that light gets bent by the sun. So you obviously have to look during the time of an eclipse, but okay, now I'm pushing, nothing happens. Okay, now there we go. And so this was actually verified already in 1917. So it didn't take long for Einstein's basic ideas of relativity to be proven correct. So at the same time as you had these amazing theoretical breakthroughs, on the observational side, the situation was extremely primitive. So even at the time of relativity, people thought that every bright object in the sky belonged to one galaxy, belonged to our Milky Way. The idea that there could be something beyond the Milky Way started to come into play, and that people thought maybe there are island universes out there. But so it's kind of amazing that even 100 years ago, we didn't know there's anything outside the Milky Way. So think about the tremendous progress. So in fact, there was a, in the 1700s, Charles Messier was a comet hunter, and there were all these nebulous objects in the way of his studies that he found these things irritating, so he cataloged them. Well, guess what? This is now called the Messier Catalog of Galaxies. And we still use this catalog. In fact, M31 is Andromeda, the nearest galaxy to the Milky Way. So it's kind of astonishing that even 100 years ago that people didn't realize these are galaxies. So who was it, or what kind of historical events happened to change this picture? Well, one of the key players was Edwin Hubble, who was using the telescopes above Pasadena. There's mountains above Pasadena that are as high as the Rockies, but there's no snow. But there are telescopes up there. And he observed, first of all, he proved that some of the light that you're seeing is too far away. It must come from galaxies beyond our own. Very huge discovery. And the second, perhaps even huger discovery was, well, he looked and saw that the light that he saw was you know what the wavelength of the emitted light is from atoms, but that light has clearly been stretched. The wavelength has become longer between the time of emission and now, and so the conclusion is the universe must be expanding. So that was 1929, and at that point Einstein, of course, had to abandon the static universe. The universe is expanding. So everything is moving apart from everything else. Well, I mean, not you and I are not moving apart, but you have to go on large enough scales for this to be true. You have to escape the local gravity. So what do we think the story of the universe and its beginnings looks like? Well, this is the hot Big Bang. The universe started, the part that we can understand anyhow, started 14 billion years ago, a number that we know quite accurately at this point. And it started as a primordial soup of quarks, leptons, photons, particles, that were all very, very tightly packed. The universe was hot, dense, and it has been cooling off and expanding from the time of the beginning. So here's it's a simplified picture of the universe, a piece of raisin bread where the raisins are supposed to be like the galaxies, and they're moving apart from one another simply because the underlying space-time is stretched, not because they're running away from one another. But there's one big difference between the raisin bread and the universe, which is the raisin bread has a center. The universe, it is thought anyhow, does not. So from our point of view, other galaxies are moving away from us. Whereas if you go to another galaxy, it'll look exactly the same. Again, things are moving apart from that galaxy. So taking this one step further, if we look backward in time and everything gets more and more compact, then everything in this room, as you go back in time, will be at one point. But what if the universe is infinite, which is very plausible? Well, things out at infinity, no matter how close you bring them in, there'll still be something out at infinity. So in short, people have this notion that the Big Bang is explosion from some point, but that's not the right way to look at it. In fact, the Big Bang is more of a point in time rather than a point in space. So it's not an explosion either, but if you want one, please put one everywhere. Well, at the time of not long after Einstein, people were aware that there's three possible geometries of the universe, which also have three possible long-term evolutions for the universe. And these would be, the universe would look like a saddle, that you'd be sitting on the surface of a saddle, or the surface of a sphere, the one on the left, or then the simple one, flat geometry, where by flat geometry, I don't mean the universe is flat, I just mean that 8th grade geometry, the geometry you learn when you're 13 years old, you can still use it. Angles and triangles add up to 180 and so on, no curvature. So this was unclear, and here's another picture of the kind of thing that happens, just for fun, in these three different geometries. So if you live on whoa, I'm not touching it, I swear. If you live on a sphere, then you'd send out two parallel light rays. They would come back and bite you from behind. So even when I was in grad school, the idea that we would resolve this question of which of these is correct seemed very far off in the future. And I certainly didn't see it coming. I don't think any of us did. That at the turn of the millennium, we had huge breakthroughs. So the data that we've been given over the past 15 years has been really staggering. So we know now the geometry of the universe. I'll tell you a little bit more about that, which correlates to what is the total mass energy content of the universe. So we really understand basic physics all the way out to the edge of the observable universe, defined as the farthest point that light could have gotten to us in the age of the universe. But we certainly have a lot of unanswered questions, like we have no idea what the universe really is made of. So on this subject of geometry and total content of the universe, we got this from the microwave background radiation, which is the leftover light from the hot early days of the universe. So in the very hot early days, you had photons moving around and bumping into things, and the universe was opaque. But once the universe became about 400,000 years old, suddenly those photons are free to move. There's nothing for them to bounce off of anymore, and we call that the time of last scattering. So when we look, this microwave radiation was first found in the 1960s. They actually scraped out pigeon excrement out of radar dishes because they couldn't get rid of it. Anyway, but so it turned out that it was this light from the Big Bang from 400,000 years after the beginning. That's really far back. Well, there's basically a ruler stick we have at the time of the last scattering of photons, And from the size of that ruler stick, then you can learn about the geometry of the universe. So you see the straight lines. If the universe has a flat geometry with no curvature, then those straight lines would be typically you would find a lot of power on 1 degree angular scales. And whereas if the universe has a different geometry, then that would be on a 1/2 degree or something smaller, and so forth. And so, although I don't have time to explain this in detail, this has been resolved, and the answer is, I'm just going to go ahead to some of the data now. This was an early balloon experiment at the South Pole, and if the geometry of the universe is flat, then you expect those hot spots shown in blue to be about 1 angular degree in size. And so these are early experiments, and this is the latest. This is from the ESA's Planck satellite in 2013. It's the size of those little red regions that counts, and they are 1 angular degree in size, and this is known to extreme accuracy, and what that tells you is the geometry of the universe is flat. No curvature. We're not on a sphere or a saddle. We just have flat geometry. You see that peak at 1 degree. Okay, so again, I don't mean the universe is two-dimensional. So take a cube and take each side out to infinity. That's sort of what the geometry looks like. Now, because of Einstein's relativity, as I said at the beginning, the geometry is connected to the mass and energy content of the universe. And here's the answer. That, if you go out past Earth, Mars, keep going into outer space, then the average place in the universe has that density, 10 to the minus 29 gram per centimeter cubed. So that's outer space. Compared to water on Earth, which is 1 gram per cubic centimeter. And I tried to explain this to Queen Sylvia of Sweden once, but I don't think I succeeded. Okay, so I have to include a joke. So these are the same data, but this is the previous satellite, WMAP instead of Planck satellite. And you see those are there we go, Stephen Hawking's initials. Okay, I just want to be sure you saw, that's important. Okay, well, so we know that we've learned an amazing amount, but here's the question that remains, which is, what is the universe made of? And the weird fact is, if you take everything that we know, your body, the air, the walls, the chairs, cocktails, throw in stars and planets, all of that is made of atoms, of atomic material, but all of that only adds up to 5% of the universe. So here's the pie chart of the universe. And normal matter is only 5%, and we have 25% dark matter, 70% dark energy, and these are the kinds of, this is what I'm working on, is to try to identify what these are made of. We know exactly how much there is, but we don't know what they are. By the way, I've written a popular level book called The Cosmic Cocktail about this problem, and here's your cocktail. So if you had sorry, it's in ounces. If you had a 10-ounce cocktail, you'd have roughly 3 ounces dark matter, 7 dark energy, and then a bunch of other stuff, even a millionth of an ounce supermassive black holes. Okay, so this is really strange. This is the dark matter problem was identified actually maybe even earlier than this by a Swedish astronomer, but certainly by Fritz Zwicky in 1933, who looked at a cluster of galaxies and saw the things are moving around too rapidly. Something is pulling on galaxies, and I mean, gravity is, something has to cause the gravity, and the stellar material he knew about wasn't enough, so he postulated some additional material, dunkle Materie, or dark matter. By the way, he also, in his book, called his colleagues spherical bastards, because no matter what direction you look at them from, they're still bastards. And then I was doing a radio show, and some woman called in. Her name is Barbarella, and I said, "Oh, hi, Barbarella." Well, it was Barbarella Zwicky, his daughter, who was still bitter to this day that people didn't listen to him about this problem. I'm serious. And so, well, we certainly do now. I mean, this is one of the oldest unsolved problems in all of modern physics. So it's a big one. Okay, so it was in 1970s that Vera Rubin and collaborators really nailed it. They saw this same behavior in every galaxy. Things are moving too rapidly. And so there's apparently dark matter everywhere. It's ubiquitous in every galaxy. So our galaxy, I'll show you a picture at in the top there. The central bright thing is meant to illustrate the supermassive black hole that weighs about 4 million suns. And then you have spiral arms of structure where all the stars are located, including the sun is 25,000 light years out from that central black hole. But when you look at that, that's nothing as far as the total galaxy, because now look at it from the side, and that is a flat plane. We call it a disk, situated in a much larger, giant, spherical halo of dark matter. So almost all the stuff is in the form of dark matter. Dark just meaning it doesn't shine, and no electromagnetic forces. Okay, so in the interest of time, I'm skipping ahead and going straight to the question of what is this stuff made of? And it is not rocks or dust, it's nothing ordinary. We have ideas, and the best one that we have is that it's something called weakly interacting massive particles, or WIMPs. So here, billions of these things would go through your body every second, but you're not noticing because they do not have electromagnetic forces, they do not have strong forces, they do have gravity, and there's only one other fundamental force, that's weak interactions, responsible for some types of radioactivity. So if you have particles with these types of weak interactions, they make really good dark matter candidates for many reasons, and we're looking for those. And they weigh about 1 to 10,000 times as much as a proton. So we're looking for these in basically pretty much 3 different ways. And I don't have time to tell you about all of these. This is one way is to go at the particle accelerator at CERN. You make the dark matter. And great pictures of, and here's Peter Higgs. So the one thing that has happened at the LHC is the discovery of the Higgs boson. It weighs about 125 protons, and it is the last missing piece of the standard model of particle physics. So we're done, standard model. But we know there has to be something more out there, and we do think that's where the dark matter comes in, and the LHC, Large Hadron Collider, is looking for it. So you create dark matter in the LHC. Nothing found yet, but ongoing research. The second way, and here this is something I helped to get this field started, is the direct detection laboratory experiments, where you put your detector and you wait for these dark matter particles in the galaxy to hit your detector. You have to go, unfortunately, deep underground to get away from cosmic rays, and now you've got a worldwide effort, and there are some hints of detection, and we'll see what comes of that. So the third way is indirect detection, where these WIMPs are their own antimatter, they annihilate, and you look for the signals, and one of the possibilities is, well, you have three things you can look for: neutrinos, gamma rays, or positrons, and we did hear earlier today about the AMS, this experiment on the International Space Station, which does have an excess of positrons. Sadly, it really is not from dark matter, okay? So it's probably pulsars or cosmic rays or something else setting it off. Now, the AMS detector has the capability of doing a lot of interesting science, but I don't think it's solving the dark matter problem. I'm showing you our searches ongoing for dark matter, and I haven't had time to tell you of the anomalous signals that have everybody excited. Maybe we'll be there very soon. What about this big beast, the dark energy? So I have only a joke to tell you about that, because the reality is we have no clue what that stuff is anyhow, so I might as well tell a joke. So on the right side here at a panel in New York, there were 3 of us women who were talking about dark matter, and the 3 men on the left talking about dark energy. And let me make the distinction. What is the dark matter is attractive. It feels gravity. Dark energy is causing the universe not just to expand, but to accelerate. So there's some effective repulsion going on here that we don't understand. Okay, so there's my joke. And with that, I'll stop.